So, okay, yeah, like I said, we're going over the last question on the practice exam. The practice exam said, hey, okay, so get and set methods for linked lists versus array lists. Array lists are great at doing get and set because all you have to do is just simply it uses the formula that exists underneath the built-in array. Let me just go ahead and open up my what I'm working on right here for a second while I pull up the other thing, GitHub.
When you're doing that, everybody did get a chance to actually look at the practice.
Yeah, sorry, this is going.
Questions, right?
Yeah, this is going slower than I would like because of having to restart
It's
teaching.
okay. I'm pretty good at it.
Yeah, well, I want to make sure I have plenty of time to hit everything in this end.
Oh, I'm pretty sure we will. Plus, also too, it's like we will be available for questions too, as far as when it comes down to the practice.
Not destruct, it's the teaching folder. Teaching, destruct, exam 2, sorry, exam 1 practice. There we go. Okay, there we go. So let's see, lists. So preliminaries, array, right? The way that things work in an array is that it's able to figure out where in an array you want to go by just using a basic formula. The array typically holds a memory location, remember? And that memory location is index 0 of the array. If you print out an array in Java, it will show you like an array of integers, it will be I, bracket, at, and then memory location. That is what you print out when you just natively print out an array. What it's doing here is showing you where to find that. And then to get to any index, you just it takes the provided index, multiplies it by the size of whatever the array is holding, and so it's able to jump to that. So figuring out in any array how to get to an index takes a multiplication operation and an addition operation. That's it. Just those two things. That's constant time no matter how big the array is, because it's just able to jump. I worked through an example here in the textbook, but it's not really important. Just simply know that getting to a specific location in an array is constant time. So for array lists, getting and setting is a constant time operation. Okay? Right? So we're talking about this here. We're talking about get set. The next thing we should talk about is the memory location, memory usage. And that one is a bit more robust of a conversation because it's not necessarily something you have to think about. They both waste about the same amount of memory in terms of O of n. In terms of big O. It's just a matter of how they do it. So with an array list, it basically every single item in an array list, if you think about it, is right. It's not actually unless you're storing primitives. You're not actually storing the items in an underlying array. What you're doing is you're storing a memory location, the memory location at which defined each of these items, right? It's a weird way it's weird, but I mean, like, it's efficient enough for the computer to handle. So each of these are, I think, 32 or 64 bytes bits depending on these configuration. Let's go with 32. 4 bytes. Doesn't really matter for this, but we're going to go with each of these as 4 bytes. Now, with an array, so this is about as efficient as it gets in terms of storing stuff, except for the fact that with an array list, right, what do we have? We have this entire extra space that's allocated for us, extra capacity for this array list. So with an array list, you waste some memory by having this extra space. And when it fills up, and you add another one, you double the size. Sometimes you increase it by just 50%. It just depends on the implementation, right? But you waste some more memory. But basically, at all times, most of the time, you're going to be wasting memory with an array list just simply by having a bunch of unused memory for adds and removes. Now, in Java, you can get around this by doing this. Once you've figured out you are full, or you figured out, or you just know from the way you're writing your program that you're not going to have any more items to add. And this is only really useful if you've got like millions of items or something like that. You can use list.trim, I believe is the term. I believe that's the function. You can look it up in the documentation, but there is one that basically shrinks the capacity of the array, of the array list. The way it does that is, of course, it makes a new array list exactly the size, a new internal array exactly the size of the original of the number of items it's storing. So it just copies all those items over, and so you've got a completely filled up array, no wasted memory. Linked lists don't have that wasted space. Instead, they more have overhead, right? For, again, this array list, we had basically a slot, and each of these had a memory location, which is a bit of overhead, right? You have to have a pointer to the item itself rather than the item itself is stored in the array list, but that's just the way it's going to need to work. For a linked list, which is made up of nodes, right? All right, let's actually look at a single node in a list, right? Let's zoom in on it. You have, just like the array, so just like the array list, this is a single index in there. You have a pointer to the item, item. So you have the memory location of the item, right? However, you also have a node next and a node previous. So for each pointer, you basically have two more memory locations you're storing. So you're storing basically 3 times the memory locations that you would for an array list. So you're using about 3 times as much overhead as the array list. Which one's better? I mean, array lists are pretty much natively implemented for most lists, just because that's how we think about using lists a lot of the time. It really, again, just depends on the context. Which one is better? If you know exactly how much, right, you can always trim with an array list. So memory usage is rarely kind of the reason why you're going to be deciding one over the other, because memory is cheap. Let's talk about add, remove now. Add and remove. And for this, we really only need to look at add, because adding is the more complex operation, believe it or not. Why? Because with the remove, you generally don't have to resize with an array list, right? But they generally take the same amount of time. So let's talk about add for an array list. To add for an array list, right, there's a couple different contexts, right? Adding anywhere except the end, add to not end, right? Adding to not the end of the array list takes O of n time, right? Adding to the end takes, and this is the thing that most people get wrong, which is that they forget this bit. Adding to the end takes constant time except in an array list. Except when? Yes? When you have to reallocate, in which case it takes O of n time. So if I were to say, needed to say this in a single sentence, I would say adding to an item to an array list takes O of n time, except when you add it to the end, except if you have to reallocate, in which case it takes constant and O of n time respectively. Gosh, respectively is such a good word there. Okay, so you can summarize what I'm saying here in very short. I don't need more than a couple sentences for each thing. If you're writing a giant essay, it's more likely you're introducing inaccurate information, right? So you want to keep it short, keep it to what you know. If you say I know this part but not this part, that's fine. I'll be a bit more lenient as opposed to you trying to BS me. Okay. Now with a linked list, either ends, right? The head or tail of a linked list is constant time. In fact, if there's something called the Big O cheat sheet, which you'll find online, and it says adding to a linked list is constant time. But it's constant time to do the add or remove physically. But you also have to seek. You have to get that index when you're doing. You also have to get the index that you're adding or removing. In an array list, this is constant time. In a linked list, that's O of n. So basically, anywhere else. Yeah, my handwriting's terrible. Anywhere else, O of n. So adding to the head or tail is constant time. Anywhere else is O of n. All right? So now that part...
We got a question on it.
Yes?
For the exam, can we... Actually, I think I already asked you this question, but we can assume that there's a a head and a tail?
Yes.
Linked list? Okay.
You can, you can assume, you can there will always be a head. You can assume that there's a tail if you find that most convenient.
Okay.
Okay.
You can't assume that there's a pre, because that would mean it's doubly linked.
Yes, I mean, if you want to write all the extra code for a previous, you can, but because in the sense, like, if you want to make it a doubly linked thing on the exam, sure, but you're gonna have to then you're gonna have to basically write twice as many lines of code, right? The intention is that it's singly linked for a lot of these. All right, let's go through this. So, I'm not going to bother going through this one too much, except to say, basically, as long as you're not going out of bounds, you can cancel the next and preves. Okay, so D, prev, so I guess I am going to go over it. So cancel these out. You've got D.prev.prev, that's B. C.next.prev, that canceled out, so C.prev is B. And wouldn't you know it, also the answer is B here, because we just simply cancel out next and prev, prev, next. That's also B. I am the person who sometimes does, in a bunch of true-false questions, just makes them all true because I'm a jerk. Yes.
If you were to go out of bounds,
Then you would write error
okay.
because these would have to resolve, and that would be an issue. Write a sequence of commands that will remove the chain of a remove the tail of a doubly linked list. So let's go ahead and open up IntelliJ. The important thing here, though, is the drawing. That's going to be a small part of the exam, just simply being able to say, here's some code, draw it, please. Let's go ahead and recent projects. No, I guess it didn't like me restarting that. Jeez, okay. This one, no. Okay, new class. And this is going to just take a minor amount of setup on my part, which is to say I need to make a private class node, specifically a private static class node static class node, a node E next node E prev E item public class node E item this dot item equals item, and that's basically all I need to do that. What am I going? What's wrong? What did I miss here? Can I duplicate class node? Right. Is a constructor, I don't put the node with the class there. That's autopilot for you. Okay, so the code for creating, so let's assume we have a node, right? Node n is equal to new node null. It doesn't matter for the purpose of this, but this is the remove the tail of a doubly linked list. Okay. Go ahead and call it tail just so that I can show you, right? None of this is what to pay attention to. This is the part to pay attention to. Tail, to remove the tail, we would basically go tail dot we would say basically tail is equal to tail dot prev, right? We make the previous tail, the previous item, okay? And then we would say the current tails dot next is equal to null. And because nothing will now be pointing to the tail, that's going to get garbage collected. Okay? Doing it with the doubly linked list is very nice and short and succinct. Using the list with 3 nodes, draw what happens, right? Okay. 1, 2, 3. Let's go ahead and confirm to make sure that I didn't miss one. I feel like there should be another line there. So we've got our tail. tail is equal to tail.previous, tail is equal to tail.previous, so that becomes the tail in the next step. And then we say tail.next is equal to null. Okay? Yeah, that seems to work. Tail.next is equal to null. It doesn't make this null, it makes this pointer null. It makes this pointer null instead. Okay? So that end up getting garbage collected. Write a sequence of commands that'll add a new item to index 0 of a doubly linked list. Yeah.
For that question we just did, are we expected to handle cases where like the list is empty?
No. No, I generally, that's why I say why I specify with a, for all these questions, I specify how, like, with a linked list of this nodes. But you're right, for this one, no. Just, you can assume that it's not empty.
Okay.
Write a sequence of commands that'll add a new item to index 0. So for this one, right, that's something along the lines of the index 0 is the head. So we would say head. So we would have this node, this new node, adding is equal to new node. And again, I'm just creating it null because here, right, normally it'd be like some item or something. What goes inside the node here doesn't really matter for the sake of this question. What the question that we care about is a new item to index 0. So we have this item there. The first thing we need to do is attach this new node, right? Adding dot next is equal to head. Let's go ahead and say head, and then we're going to do head dot previous is equal to adding, right? So this connects it fully, right? So let me just kind of work on this part and the next part at the same time, right? We've got this, I think 3 nodes again, I said. The problem? Yeah, 3 nodes. So we've got this case here, we've got, right, this is adding, this is head. First thing we do is the first line was this. Adding dot next is equal to head. Head dot previous is equal to adding. And now the third step is that we basically update the labels in this head so that everything makes sense. Sorry, in this list. Head is equal to adding. And that's good. That's all we need. All right. All right. So let's get into the actual coding. This one's fairly straightforward, just to kind of a reminder. That's why it's only worth 5 points. This is definitely easier than what would be on the exam, whereas this one is, I'd say, a bit harder. I actually made a new question last night for this before I sent it out to get printed. Okay. Let's go ahead and remove this. We don't need it anymore. We will go ahead and import. So this basically asks, hey, we've got the minimum, you want to find the minimum and the maximum of the list and add them together. Right? So grab this. The reason, also, anybody know why I do integer.max value and integer.min value over here?
So whatever you compare it to, like, always be like less than order?
Yeah. If you set your smallest value to, if you set the initial value of the smallest thing to be the biggest thing ever, anything you find is going to be smaller than that, or equal to, right? Similar with the max, anything is going to be bigger or greater than or equal to it. So those are safe values to set it at. As opposed to like setting it to 0 because it's possible to have negative numbers, or it's possible that there are no positive numbers in a list depending on the configuration. So that's why I set it up like that. So finding the minimum and the maximum is fairly straightforward. We have done this, you have probably done this a million times. I'm not even going to bother writing a regular for loop. I'm just going to do for each. For int num in list, right? And if num is greater than min, then min is equal to num. And then we see this for the max as well. If num is less than max, sorry. Wait, no, greater than the max, greater than the max, less than the minimum. So if number is bigger, if this number is bigger than the biggest number we found, num, and if it's smaller than the smallest number we found, we do that. It's possible our first number's both things, so that's why I don't do an else if, right? So return min plus max. All right, this one's fun because suppose you have a list of some string. Write a method called reverse word that creates a new list with all the string reversed. Now before I forget, for this algorithm, I will go over these in a second, but for these, on the exam especially, if you see one with the remove method, or requires you to remove stuff from a list, remember the whole thing about that you learned from the last problem in your exercises, that when you remove an item from a list, everything shifts, okay? So, what we're looking here is that we've got something, hello world nice, and I always give you input-output pairs. If it's something that I think is ambiguous, I'll give you multiple input-output pairs. But here, basically, we're not reversing the list itself, we're reversing the individual elements in the list, right? Hello world nice, Ole, Drulau, and Eken. Okay. So let's go ahead over here. Now, is there a reverse method built into Python? I always forget. Or not Python, into Java.
I think it is Python. I don't think it's Java, because I remember we had to do that for one of the, I think it was one of your exercises for Python.
List output. This is almost always what I name my return value. New array list. And return output. Oh, can't spell today. All right. So once again, we can use the for each to go over here because we just don't care about the index. So we can go for, if you care about the indexes and you have to remove stuff, the fact that I'm mentioning removing stuff, and this is the second time I brought it up, we call that a hint. So for string word in list. So if you have to remove stuff, you will care about indexes, is the point I'm making. String word in list. For every word in there, basically we'll go ahead and do this the manual way. Reversed is equal to, we'll create a string reversed, right? I've got to declare types here. I do Java and Python in the same semester, so often I forget I have to do one thing versus another. Okay. Let's see is there something I can do here with word dot. Is there a reverse or no, I don't think there is. Boo. Okay, we'll just have to do it the boring way. Okay, and this is a bit of a pain if I want to do a for each loop with this one, because you can't say for each car letter in Word, right? Can't do it like that. You have to do this. If you did this on the exam, if you've got to do this on the exam, whatever, I might circle it, might deduct half a point, but you need to do this if you want to iterate over a string using a for each loop. You have to use two character array. And if I just simply did this reversed plus equals letter, let's go ahead and be more specific. If I just simply did this, this would give me the exact same, right? Reversed would be the exact same as what I previously have. And so the solution is either I have to go reverse through this list, through this string, right? But I've already written this code and I feel kind of committed. So what I'm going to do instead is I will reverse how I add it, which is I will say put letter in front of everything else that we've already added, right? It'll put H, and then it'll put E to the right of H, then it'll put L to the right, it'll put an H, then E to the left of H, then L to the left of E, and another L to the left of that L, right? So it'll build it going this way as opposed to building it going this way. And then what we're going to do is we are going to say word list dot add word, not word, reversed. That would have just simply been useless. It would have wasted everything I did there if I just added word. Okay, so we create the reversed word and then we add it. Great. For both these questions, we have the bottom question of what is the runtime for what you just wrote. It's generally just a low amount. Remember, you are not writing anything constant time, so the answer is always O of n or O of n squared on this exam, unless you're doing something weird, in which case you know what you did. So over here, we're going through each number once, checking each number against two other numbers, so maybe two operations for each number. This is O of n, right? It doesn't, if I were to make this, and the easiest way to think about that is if I double the size of the list, I'm going to do twice as many checks, right? So with this one, the question in this case is what in the world is n? If you consider n to be the number of strings, for each string we have to reverse it, O of n time, right? If I have twice as many strings, I have to reverse twice as many strings. I'd say the more accurate way to think about this is the number of characters that are taken as input, because strings are of variable length, right? Some can be long, some can be short, but even then it's still O of n because you go through every single character once, right? You take that character and you add it to a new string. So again, we're looking at an O of n time because twice as many characters, twice as much work. All right, so here we've got this linked list. Deleting a list is fairly straightforward. Let's go ahead and just draw this on here, okay? So this is kind of interesting. If it was just simply a singly linked list, all I would have to do is this, which is say size is equal to 0, and we're going to have to do that no matter what, okay? Because if we're deleting the list, size is going to be 0. And then if I simply said head is equal to null, that would mark it for garbage collection. And so the first item in the list would get garbage collected, which would then say, oh, nothing's pointing to the first item to the next item in the list. So garbage collect that. Then nothing would be pointing to the next item, so garbage collect that. The way garbage collection works in Java is that variables all store something as a memory location, and Java keeps track of how many things are referencing an item, how many times this is stored. When that drops down to 0, it says, aha, nobody cares about this anymore, so I'm going to garbage collect it. So, however, because you have a previous here, right, because this is a doubly linked list, we need to be a bit more thorough, right, which is that we just simply have to, we'll have to do something along the lines of this. There's a couple different ways to do this. I could say head is equal to, let's see what I could do here. I would say basically, current, I'd basically create that current loop and say, let's see, I'd say basically set up a current is equal to head, right? Current is equal to head. So node current is equal to head. While current is not equal to null. Current dot previous is equal to null. We set the current dot previous equal to null, so nothing's pointing to that. And then I would say, let's see. Question is, and then let's see, if I did current is equal to current, yeah, if I did current is equal to current.next, never mind. This is turning into a nightmare for writing this. Okay. Let's go ahead and do this again over here, PSVM, right? We've got, so it would look something like this. Let's see. We can start out, you know what? No, we'll start out with head. Wow. Head is not equal to null. Head.previous is equal to null. Head is equal to head.next. And then head.previous.next is equal to null. Make sense? So what I do is I say, hey, the thing behind me, can't do that quite yet. While the head is not equal to null, so what we're going to do over here is, while the head is not equal to null, I'm going to advance by 1. Head.next. In that case, because we're going to head.next, we're going to say, while the next thing is not equal to null, we're going to advance it, and I'm going to say, hey, the previous thing, its next is null, and I'm going to delete that, and then I'm going to delete my reference to him. And I'm just going to keep doing that until I get to until the head and the tail are the same item. Head is equal to null. Tail is equal to null. I haven't done this one since last semester, so of course I forget. And then the semester before that, and the semester before that. Size is equal to 0. And there's a lot of different ways to do this. I'm not going to waste more time on it because of the 3-pointer. Okay. This one is much more interesting. So, by an instance method called count, count iterates over a linked list and returns the number of times the item occurs. Okay. Right? So, just so that I can finally deal with those errors, just not. Okay, here we go. Public node E. Obviously, this is not really a functional list, but the point of it is that we are just simply just trying to get this answer as though it were written in the linked list class. We don't take in anything, this one, except what we want to count, which is E item. Okay. So let's go ahead and say we need let's figure out what our answer is first. Total is equal to 0. We're going to count how many times that item occurs, and then we're going to return 0, not 0, a total. Right? You can tell I really don't like having errors in my code, which is why I program like this. I like my code being able to run at all times. Next, we start out with, this is a very common thing, as you're seeing. Node E is equal to current. Sorry, node E current is equal to head. Basically, we start out the head. And we say, and then the question is, you always have to ask yourself when you're doing this, basically going through one at a time on the list using current, is, am I doing current while current is not equal to null? Or am I doing current.next is not equal to null? And the question is, do you care about are you comparing yourself to what's in front of you? Oh, sorry, what the next item is. If you're comparing this to the next item, then you would do current.next is equal to, while current.next is not equal to null. If you care about checking about whether this particular node is null or not, you would do while current not equal to null. While current is not null. So while current is not null, we ask the very simple question: is current.item dot equals item. And so that goes in an if statement. If these two things are equal, total plus equals 1, and that's it. Well, not it. Then we just got to go to the next item. Current is equal to current dot next. And the important thing to recognize here is, because of the way this is, that yes, current dot next could potentially be null, but as soon as it's null, we'll get to here. We'll check this next and ask, hey, is current equal to null? Well, yes, that's a perfectly valid value for a variable to have, so long as you don't try to use it, right? To like use pointers or methods inside of it. And so you can say, it's null now, so I'm gonna stop, right? All right, write a static method that takes in two sorted linked lists and merges them. This is a static method write a static method that takes in two sorted linked lists of integers and merges them into one sorted linked list and returns it. Since it's a static method outside of linked list, you cannot access the nodes. You're allowed to remove items from list A and list B. That's an important distinction here, because I am going to be removing those items if I'm allowed to, because that makes it a lot easier.
This kind of seems familiar with the array list, one of the array list like questions from lab 2. Like, for example, when you had to compare two sorted lists or
Yeah.
compare the C. So
The permutations, you mean? Yeah.
Yep.
This one is, so, by the way, again, these are both linked lists. The only reason I write them as lists, because otherwise this would go off it would have gone off the edge of the paper. So, so knowing that they're both linked lists is important, because that means that we can manipulate the front of these lists, or the back, in constant time, right? Which means that as you'll see, this entire algorithm I'm about to do takes linear time. This is the second part of merge sort. Merge sort basically takes advantage of the fact that merging two sorted lists takes linear time. So again, I'm going to call this output is equal to new linked list, return output. So what we need to do here is we are going to merge them into one. You're allowed to remove items from both A and B, so I'm going to do so. And that's going to be my condition, in fact. My condition will be while list A dot size is not equal to 0, and list B dot size is not equal to 0. While one of them while both of them still have items in it. Once one of them runs out of items, I need to change my strategy. Make sense? What are you yelling at me about? Okay, yes, it can be replaced with is empty. Sure. So replace with is empty. Sure, fine. Okay, so while neither of them are empty, basically we got to the way that this strategy works. How much time do I have? Is that if I've got numbers like this, 1, 2, I've got 1, 3, 4, 5, 2, 6, 7, 8. Let's go with actually 2, 5, 7, 8. If I've got two sorted lists, right? These are both sorted. If I want to merge them together into one output, the way I can do this is I know that this item is going to be smaller than everything else in the front of the list is always going to be the smallest item for both lists. So I can ask which of these is the smallest, and that should be the first, and that should be the first item in this list. So 1 versus 2, right? Well, 1 is smaller, and what I'm going to do, and I could have like current counters and advance them if I wanted to, but if I'm removing them, if I'm allowed to remove, all I'm just going to do is remove the head of this list and add it to this list over here. And then I just repeat, which is smaller, 2 or 3. 2 is smaller, so I'm going to remove that, add it to here. 3 versus 5, 4 versus 5, 5 versus 6, 6 versus 7. Now we're empty, and in which case, in this case, all I'm going to do is I'm going to just simply say, well, the rest of the items in these remaining items are bigger than everything else in the list. They're already in order, so we can just simply slap them on to the end of the list, no problem. So, if list dot get zero, list A dot get 0, constant time operation because it's the head, is less than list B dot get 0. And right now we might want to ask ourselves, what if there's a tie, right? What if they're the same side? In which case I'll just simply solve it like this, less than or equal to, right? I'll say the left side takes priority, okay? Or list A will take priority. So if list A is less than or equal to list B, that means this one is less, so I'm going to do output. I'm going to do it all as one statement. Output dot add list A dot remove 0. So if the first item is smaller, remove it and add it to my output. Else, and this is very simple, output dot add list. If the first, then because of the way this logic works, if it's not the front of list A that's smaller, it's going to be the front of list B. There we go. And then, not sure why it's telling me, hey, can be replaced by the remove first call, can be replaced by get first. Bunch of weirdos writing this now. Okay. Okay. Let's go ahead and so now one of these is empty. We don't know which. We could do an if statement and ask if A is 0, then, but I'm going to be lazy. List A. What we're going to do is we're going to do output dot add all, which basically says, hey, everything in here, we're going to add it to this list. So I'm going to say add everything from list A. If list A is empty, that's not going to do anything. And then output dot add all. And if, for the sake of argument, it's list B that's not empty, it's going to add everything from list B in. So overall, not too long to do this. Make sense? Questions on this one? I'm going to keep moving pretty quickly. So again, if you need to copy this down, just refer back to the video. I'll post it basically as soon as this lecture is over. Runtime complexity of this algorithm, because we're doing constant time operations on the front of the list, and we're doing it to every item. This would be O of n. Technically, so just FYI, technically when we have two lists and we have no assurance that they're the same size, technically the time of this would be n plus m, because the idea is that one could be drastically bigger than the other. Honestly, though, assuming that they're both relatively the same size, you can say they're O of n. This is not the role of my class to teach that. It's the role of the other classes. Okay. Write a method that reverses a doubly linked list. This method will be an instance method of the linked list, so you can use the node, tail, blah, blah, blah. So this one is worth looking up, because it is the beginning state of an interview problem, where basically it says, what if you go from a doubly linked list to a linked list, right? I'm just going to, it's worth looking up, because eventually you get to the point of how do you reverse a linked list, a singly linked list, without using any auxiliary data structures, meaning without using any extra lists or anything like that. Because, as I'm about to show you, if there's no restriction on using additional data structures, a lot of problems become trivial. List E versor is equal to new linked list. And all I'm going to do is say for sorry, you know what? I'm just going to be silly. While this dot size. It didn't set up a size variable, so let's set up that now. Int size is equal to 0. This is part of the reason why it's on paper. You get to ignore all this nonsense. While this dot size is not equal to 0, while there's still items in the list to remove, what we're going to do is we are going to say reverser dot add to index 0. So we're going to take advantage of the fact that you can do index 0, and then we're going to do this dot this, I don't have a remove method, whatever, remove 0. Make sense? So we're going to remove the initial item, add it to the, and then we're going to add it to index 0, right? Because adding to the front, continually adding to the front will reverse something. This will eventually empty out while this dot size is not equal to 0. And then once it's emptied out, what we can say is for e item in reverser, and this will go through, this will iterate through it in O of n time, and is basically, that's the point of the iterators. They go through a linked list and or array lists in the most appropriate fashion. So it's not going to cause so it's not going to run in O of n squared time just from doing continual get calls. So this dot add reverser dot remove 0. And we will go ahead and create method. Great. Why am I creating these methods here? So that I can just not have to deal with the errors. Again, completely non-functional methods, but the entire point is not to write functional methods here, it's to write a functional answer for the addressed question, right? I'm not making the class from scratch, except in this case, which we'll make a new class right now to start it, okay? So suppose we have a new type of linked list called a sorted linked list, which is a linked list, but keeps all the items sorted. As a result, when we add an item, we're not going to give it an index, we're just going to give it an item, and it figures out where to put it, okay? So the idea here is that we're making this add method. We don't have an add method, right? We're just making it from scratch here, okay? We can use either a singly or a doubling linked list. I'm going to use a singly linked list because that's going to make things simpler. You can use greater than, less than, or equal sign to compare items, but if you do remember how to use compare to, you can do so for extra credit. You cannot use this. And cannot use these methods. The solution must run in O of n time. So let's go ahead and create this class. This is probably of all the other questions the most important one because it's basically making the add methods from scratch, which is a good way to, except it's a completely different context. Sorted linked list. All right. And once again, what we're going to do here is this is probably going to annoy me because it's going to give me this import statement. I'm going to say, no, I don't want to import things, right? Just like everything else. See what just happened? It tried to be super helpful. Paste, special. Paste is plain text. There we go. So I'm going to keep this simple for everybody. We're going to go node, no e's here. Okay? Because what we'll do is we are just going to do a int. We're going to do an int item. That way we can use less than or greater than. That way it's going to be easier for everybody to read. Also because I'm going to make you work for your extra credit. Make sense? So we've got, and this is basically if I was going to give you code to start with, it would look like this. Public, void, and yes, on the exam, it said, or practice exam, it said e item, but in this case, we're doing int item. When we're working on paper, we get to ignore some realities, right? Like the types, and just simply use less than, greater than, right? Here, though, in order to make sure that it's going to be nice and working, we got to do this. All right. So we've got our node. We've got next. We're going to not bother with previous. Okay. So let's go ahead and figure out, whenever we're dealing with add or remove methods, we need to figure out like base cases and stuff like that, because we want to handle those first, which is, in this case, right? And so running through our list, let's think about what's relevant through the 5 cases that I'm typically, because there's a maximum of 5 cases, right? From the doubly linked list, and I don't think we're going to hit them all. For instance, the first case, checking if the index that we're adding to is out of bounds. There's no indexes here that we have to worry about, right? We're not declaring any indexes, so we don't have to bother checking about that. The next thing is, what if I'm adding to an empty list, right? Right? In that case, there is no head, there is no tail, so in this case, we should cover that. We can either do it like this, if size is equal to 0, or if head is equal to null. Either way works. And I'm just going to do this over here so I don't forget, size plus plus, right, at the end. It's going to be super minor if you forgot that, but it's not. You forget that, that's like accidentally flipping a negative somewhere and then doing all the math correctly. It depends on what the math professor or physics professor feels about that. And for me, it's not that important of a thing as long as the rest of the work is correctly done. So if the head is equal to null, that makes sorting it rather easy. That means that we are going to, that also means we can just simply go node adding is equal to new node item right over here, because they were always going to throw that into a node. And we're going to say head is equal to adding, tail is equal to adding. And I always end up logicking myself through this in a different way every time I do this. So it's just to show there's a lot of ways to get to the correct answer. So let's see. The head case, adding a new head would basically be saying, hey, if this is if this is less than everything else in the list, right? Let's go ahead and just like draw these out, right? Let's say I've got 3, 7, and 10. And the good thing about this is we should always assume that this sorted linked list is going to be in order. After all, we're making the add function, so we can assume that our add function is working and keeping everything in order. If things were out of order, then we might as well just throw up our hands and surrender, because that's not going to work. So we've got 3, 7, 10. If I add, this is the head. I'm just going to put H over here for the head. If I want to add 1, right, when I add 1 here, right, I'm going to have to create a new node, connect it, and make that the head. But that's about it. Okay, the other case is, the other kind of weird case is adding a tail, right? Adding a new tail would basically be if I'm adding 20 or 100 here, in which case I add that to the end, take the old tail, connect it to the new thing, stays there. So yeah, I'm going to go ahead and say we're modeling this off of basically our 5 cases, right? So don't have to deal with that, right? Case 2, which is what if it's empty. Else if, and we need these to be else if so that we don't accidentally hit other ones. Else if head let's say else if let's say, yeah, we can always just keep using item head. Item is less than head.item. In fact, let's make it less than or equal to, because that's easy for us, right? less than or equal to because, right, if I'm adding in another 3, then that just becomes connect that 3, right? So in that case, adding dot next is equal to head. Head is equal to adding, right? All that is just connect this over here and then say this is the new head. Right? Everybody see that? That's just our case 3 here. That's just simply case 3, adding new head. If one other thing is that you don't need this additional case over here if you don't have a tail, right? If you don't care about the tail, you don't need this other case over here. I just find it's not going to really hurt us or help us either way. So if the item is greater than or equal to the tail, right, we're just going to do it like this because even though we can handle an equal sign, again, it just becomes very easy to do this. The numbers are all, in this case, we're working with numbers, they're all equal. Adding new tail. Oh, not greater than equal to tail. That's a very common mistake to try to compare the nodes versus the items in the nodes. So try to not do that. Item is less than or equal to head dot item. Item is greater than or equal to tail dot item. And this is exactly pretty much the same thing. Tail dot next is equal to item. Tail dot next is equal to adding, right? See, I was just talking about doing that and I did it. Completely unforced error on my part. Tail is equal to, I'm not head, tail is equal to adding. All right, now the part that we've been avoiding, which is the else case, right? So this code is ending up a bit longer than I would like because I've decided to do it differently this semester, but that's fine. Note again that this is the 15-point question, which should give you a hint that I value this question and questions of this type. So perhaps, again, one of the things that I've mentioned is that that ChatGPT has its resource, has some, I love AI. I'm a big proponent of it. But of course, if you rely on it for coding, you're going to have issues because you're not going to be able to do it yourself. Plus, it will produce code you don't necessarily understand, which is it's an issue. So what is AI useful for in this case? AI is exceptionally useful here for me to go to the AI and go to an AI thing like ChatGPT and say, hey, I've got this exam coming up on linked lists. The professor did an add method for a sorted linked list. What other kind of questions might my professor do? That's a fairly valid thing you could do, or generating other questions for it. I actually, during COVID, when AI started becoming a thing that suddenly people were using, I used ChatGPT to generate facts about linked lists, some of which were false. I asked it to generate a collection of true facts and a collection of false facts, and then I just simply grabbed 10 of them and then basically told the students, all right, 1 point each, true or false, right, about these linked lists versus array lists. And in fact, I didn't actually have to tell it to do some of the questions. Some of the false ones did not come from the false facts list. Some of them came from the true facts list. It's because ChatGPT is.
ChatGPT.
And again, this was also 2 years ago. It's gotten much better.
Oh yeah.
All right. So how do we do this? So basically, this is going to involve us iterating through kind of the current. So this is going to involve us being able to use and make assumptions in a kind of nice way. So for instance, we know that as we're going on through this list, in the else condition, we're dealing with a subsection of the list. There's nodes where there's items that we're greater than, and there's items that we are less than. So, for instance, I might be here for 6, 8. All right, and let's just kind of check this. This is going to be my current, which I'll call cur. And then we've got our adding, which is going to be its own node, which is, let's say that's 7, okay? Okay, current. So let's say this is that we're on current. And we're going to start, and just to answer the question that's going to be asked, because it's the only way to do it, we're going to start off current being equal to head. And what we're going to do is we're going to see if we fit between current and current.next. Okay, the reason this will work is because we've already checked against head. And so we know that we're not going to be less than the item that we are currently on. We know we don't have to go here, right? That's not where we need to go because we're going to always be checking between this current item and the next item. So what we can ask is 7 less, is adding item, or is item less than or equal to current.next, or current.next item? And if it is, great, we'll put it, we found out where we need to stuff ourselves. Otherwise, we advance, right? In which case, what we would do is we'd say, oh, now this is current. Okay, is adding less than or equal to current.next item? Yes, it is. We'll go into there. And we don't have, and another nice thing about feature is we don't have to worry about going off the end of the list and hitting null. We already checked if we're going to go off the end of the list by checking the tail. If we're bigger than the tail, we know we're going to be smaller than tail. We know we fit between the two extremes. We know we fit between the smallest item and the biggest item. So we would then do adding.next is equal to current.next, and then we'd say current.next is equal to adding. So let's go ahead and do this. So node current is equal to, and again, you could do cur because it's harder. I can autocomplete. You can't. Is equal to head while, and because we're comparing against current.next is not equal to null. And we know that this is never gonna, that this loop is never gonna actually end. Because we'd never hit null. So instead, because we're always gonna be less than the item there. So we're always gonna hit our condition. What we're gonna do instead is we're gonna do, let's say, wow, I'm just gonna do the classic while loop thing, which is done, Boolean done. And if you haven't seen me do this yet, just do this, it's great. Boolean done is equal to false, while not done. And then when we're done, we'll just simply say done is equal to true. That's it. It's a dirt simple way to read this condition. So while we're not done, we'll say if current, and we can do this because we know we're never going to be hitting a null pointer exception because of the way we've set this up. If current.next, so let's see, item is less than or equal to current.next.item, then we're going to stuff it in, else current, actually we don't even technically need the else, we can even keep it simple, which is technically incorrect, but we can always say current is equal to current.next. We always want to do this. If we add the item though, we really should just like have this in an else, but as you're about to see, this isn't going to matter because we're about to do this. Done is equal to true. Right? Once we found the place to insert, we're going to insert it and say we're done. So how do we insert? So if item is less than or equal to the, let's see, we're going to be going through, right? We're going to be comparing it, and it's greater here. It's going to be greater until it's less than, right? Because we're going to be greater until we hit the point we're supposed to insert, it's really all we have to check. We don't have to check if it's in between two separate values. We don't have to check it against current. We know we're not less then we know we're greater than current because we already checked if we're about being less than it. And since we were not less than, we had to be greater. So adding dot next is equal to current dot next. And then we say current dot next is equal to adding. And that's, again, just the classic way to insert a node in between two other nodes, right? We say, to insert, we have this configuration. We have current, and then we have this other node over here, which is our adding. Okay, we say adding.next is equal to current.next. Then we say current.next is equal to adding. We just change where that points to so that it inserts. Then we say done is equal to true. We run another line, or we don't run it. Doesn't matter, because now that we're done, we stop. This runs, and the condition was that this runs in O of n time, and it does. Why? Because constant time case, constant time, having to go through almost all the nodes in this case, right? Maybe having to go, on average, we'd find our proper location in the middle, on average, right? Sometimes we'll find it early, sometimes we'll find it late. That'll average out to finding it in the middle. We have to go through half the items, means it's O of n time, right? It's going to take, or another way to look at it, if the list is twice as long, it's going to take twice as long to find our spot. So that's an O of n time. All right. And that's it for for that. So we have 7 minutes left. Let me go over some things over here. First off, again, exam is out of 105. It has out of 100 points, but there's 105 points on there. That means there's some extra credit already baked in. I will have some amount of information. Let's go ahead and pull up the actual exam for a second.